Okay, we will continue. So now we start with a close look at the example of the park. The map should be zooming to where the river crosses the city limits, and the scale should be 1 to 24,000. So now on the map tab in the inquiry group, now I'm gonna click inquiry. So right here I'm gonna click measure, again measure distance. So options, so from options I'm gonna go to distance unit, change it into miles. So the option, click distance units and miles. If necessary, we will click to clear feet. So now we are going to follow the river north about 2.25 miles, and we're going to click at the end of the river to start the measurement. So from the pointer north along the river, we do not have to drag. As we move the pointer, the segment length value changes in the measure dialog box. So when we reach the top of the map display, so assume the measurement still less than 2.25 miles, press and hold the C key to the keyboard and the pointer changes to the hands-on. So I'm going to just start from here, and I don't know where to measure, but hold it to C. Okay. Along the river, press hold the C pointer changes to hand, pan north, and release the C to continue the measurement. So when the length of the measurement reaches about 2.25 miles, double click to end the measurement. So half a mile due east of the end of the measurement is a park. Switch back to the Explore tool on the Map tab and click the center of the park where the park's layer overlap to identify the park. Same, its name is Pecan Playground. The attributes in the pop-up window from the park layer from Parkland because of the layer order in Contents pane. So, Pecan's Park. I don't know where's Pecan's Park. And I can click C to pan there. So if I'm zooming here, Pecan pan. Alright, so that's how I continue to measure. So now it's 6.5 miles. So and I just click pan to move around. So by default, the topmost layer is identified. We can choose other layers from the drop-down list under Explore. In the lower right corner of the Identify window, we will click the Zoom tool. Okay, and then which will zoom to the future Pecan Playground. So the map zooming to the park, we will create a new bookmark named Pecan Playground. So I really don't know where is Pecan Playground. So I'm gonna look, locate Pecan Playground. Right here. Yeah, right here. Okay, so now here is Pecan Playground. I'm gonna add a bookmark, new bookmark. So I'm gonna call it Pecan Playground. And the map zoomed to the park, and we will create, we did, and close the Identify window and the Measure dialog box, and we will turn the parkland layer off on a few minutes. So now I'm gonna close everything, and I don't need the Measure tool. So alright, turn this off there. Okay, how do I turn it off? Let's see. I don't want this. I don't want to locate. Go back to explore. See, alright. There was not a button you click on and off, but you can click explore and just back to the main menu. I would say that we will turn the playground layer off, on and off for a few times. Playground, parks. Is it parks? Turn the parkland. So where is our parkland? Yeah, there. We will turn it on and off a few times. Either feature confirms to the image both encroach, for example, on the surrounding streets. The parks feature seems better, however, because it includes the swimming pool and the play area at the north end of the block. We will come back to this place later for some spatial editing. We add the feature on the bookmarks, so we will click the Dodger Stadium to zoom to it, and our view is now centered at Dodger Stadium, and compare the parkland and parks layers. So now I'm gonna go back to bookmark and Dodger Stadium, and we can compare right here. See? Now we will choose the park data. We will follow the river upstream and look at some more parks to help to reach a decision. So in the contents, we will drag the Los Angeles layer directly underneath the Los Angeles River. Okay, and we will set the map scale to 1 versus 36,000. 36, 1, 2, 3. Click and start panning northwest along the river course. Oh, I think it's right here. Yeah. And we soon come to the Griffin Park, so which is right here, Griffin Park, the vast park at the river's elbow. And both the river and the city limits run along the park's edge. And notice that to the east, Grande and the north, berm bark of the city limits, there are features from the parkland layer, but no corresponding parks features. This is another case of jurisdiction, and the city of Los Angeles, which supplied that park's data set, doesn't maintain data for parks in other cities. So this difference in managing data arises a question. The new park must be a quarter mile away from existing parks. Does that mean any park in any city or just any park in Los Angeles? We will interpret it to mean any park in any city because by and large, there are no residency requirements for park use. On that basis, we should choose the parkland feature class for the analysis. We don't know if it is more or less accurate on the whole, or we only examined one park, but it covers a part of the area of interest that the park feature doesn't. So in row 6, the data requirement table under dataset, we will do parkland. So we chose parkland. So in row 6 right here, we will say dataset, it will be parkland instead of just park. Okay. So but part of the area it doesn't. So we look again parkland. So we could see this area. Let's see parks on and off. See, this park covers this area, which it doesn't. It has more those areas for this layer. And we will add more park data. Now for the new parks feature class and Vista Hermosa Park, which has been completed, but it is not a new parks shapefile, we should find out if these features are included in the parkland layer. So in the project pane, we will expand the park data folder and add new parks shapefile to the map. So I have to go back here again. Alright, so now source data, sensors, I think it should be park data. New park, and I put the new park here. So new park, we will let it zoom to layer. Okay, let's see, zoom to layer. Alright, so now those new park data added, and we will see what's going on here. Alright, so the new park we have to change into Mackay green. So Mackay green. It's right here. There. Alright. We right click on the symbology we did and zoom to the layer, and how in the contents we right click and zoom to layer. And we turn the new parks layer off and on and off many times. So let's just look there. So you can see the shining part. And on the base map imagery, but they are not represented in the park layer. Another data preparation tasking here, we will later add these missing parks into the park feature class. So now we will zoom to the Vista Hermosa Park using the bookmark we created. Not bookmark, Vista Hermosa. Alright, I think that's this park, right? I don't know. The reason is I'm gonna change base map with the labels. Yeah, this is the park. And there was no parkland feature here either. We will be looking at it. Later we will create a park featuring this location. And now in row 6 of the data preparations, we have to say we're gonna back in our document. So for away from the parkland preparation, we have to say added features. Added features. Okay, so that's how we have the data visualization here, and we have to do next is choose the census data. We decided that we would represent neighborhoods with census data. Census units, we two choices are blocks, groups, or tracts. Block groups meet all the attribute needs either directly or indirectly, but they are smaller than tracts. Block groups also portray demographic patterns in more detail. So here in row 7 through 10 of the data requirements table under data set, we enter block groups. So block groups, let's see. Okay, we have parkland, and parkland we need added neighborhood. We will say block groups. And then here we need block groups too. The same block groups. Block groups. Block groups. This one will be block centroids. And we have two more here. We need to calculate lower income. No, lots of kids. Not here. Oopsies, 11. So this will be centroids. Not this one. Cancel. Delete this, delete this, delete this. We're not there yet. Alright. So now we have to calculate. Okay. So here we're gonna do it a little slow. The rows 7 through 10 of the data requirements table under dataset, we enter block groups. So from 7 to 10, block groups, block groups, block groups, block groups, and then block centroid for 11, serving the most people. Population density and age under 18 attributes doesn't exist as such in the block groups table, but we can derive them from other attributes. So in row 8 and 9 under population under calculate. So the last analytical requirements is to count how many people live within a quarter mile of each proposed park site. We will do this by creating quarter mile rings buffer. So ring buffer is a tool that we use a lot. So quarter mile buffer, so rings the buffer around the proposed sites, and counting the census block points in each ring and summing their populations. And now we will choose the final map data. The last rows of the table list data that we may need for cartographic reasons for the final map. So row 12 lists political boundaries. Our source data has features classes of cities, counties, and states. Until we design the final map, we won't know for sure, but we can foresee a likely need for city and county boundaries, but not for state boundaries. So in the project pane under Esri geodatabase, we expand boundary. So now we preview city polygon and saw that its extent covered the entire United States. It is more data than we will need. We never review the county feature class, so do that now. We're gonna go back here and Esri. So expand boundary. I expand everything. Under boundary, we jack the county feature class to the map. So let's see if we have a county. I don't think so. So now I'm gonna do county. So county put on top. So I cannot see anything. So then I'll just say zoom to layer. And the county is for the whole United States. Zoom to the layer and look at the attribute table. So now I'm gonna right click on open attribute table. It's loading. Okay, so I like it flow. So you see it's 3,219 counties in United States for our data set. The attribute table includes the county and the state names along with the census attributes similar to those we have seen in other layers. Now we're going to turn off the county layer. Okay. And close its attribute table. So now in row 12 under preparation. So okay, right here with political boundaries, what we have to do is we have the data and we will put city. We have a city underscore p polygon. So row 12 data requirements under dataset, enter this and press enter to start a new line and enter county. So and county. And now in row 13, in the spatial data column, we need we have a need for roads listed. So roads is right here. And in the project name under the Esri table, we expand transport and drag major road to the map. So now we back on here, major road, which is right here, transport data. And we can see some stuff here, and I'm gonna zoom to layer, and we can see some roads. Wow, that's cool. And we have the road data, and then the data covers the Greater Los Angeles area, which is appropriate for the map, but we also know that roads are available on the topographic base map. So change the base map to topographic using the base map button on the map tab in the layer group. So I'm gonna do topographic. Perfect. And zooming, we can see the difference between the major road layer and the base map. Optionally switch off between the imagery base map and the topographic base map to compare the accuracy. So we have to zoom in, see the accuracy. You can see the road and it's not perfectly digitizing. And let's change the map for this road. Yeah, it's the same. See, we can also compare the accuracy. Some parts are good, and like right here, we can definitely see the road is right here. And it's just like you have to do a little digitizing a little bit more. And we'll let it render a little bit. And some roads you can see it's overpass or underpass that we have to be a little careful on it. So let's see, where is my Los Angeles boundary? And you can see there are some parts we are missing parts of it. And even the road, it should be right here. And if we zoom in, we can tell that the road is not on the road, it's on the park. That some work we have to do, and you can see those major road is not here, and it's running around over there. So the topographic base map is more detailed and more accurate. How do we know? So let's see a little bit. Topographic. Even here too, we can tell there. So the layer is also updated automatically for Israel will update it, so the maps will stay current into the future. So the roads on the base map are also already cartographically styled nicely with labels, so it will be a lot easier to work with. So one consideration with base map is that they are essentially an image. We cannot query or select from them, and we cannot use them as the input for tools. The project, however, doesn't include roads in the criteria. We simply want roads for reference and cartographic purposes. For these reasons, we will use the topographic base map to display roads rather than using the major roads dataset. So in row 13 of the data requirement table under dataset, we just do base map. That's really bad, base map. Okay, relief and imagery are also available online for base map layers. Oh, not here, not pepper. We don't have to. Final map, we will do base map, base map. Because we don't have data. Okay, and for this part, we're going to reduce extent, which means we have to do definition query. Actually, it's just definition query. Query to reduce extent. Okay. I think we are good. We will save the work. All the dataset we need for the analysis have been specified. We can save and close the work. And we will zoom to the Los Angeles layer and look a little bit, but now we have nothing to prepare more. So we will take a step back for the project analysis operations take place within a particular coordinate system, and choosing that system is an important part for setting up the project. To make a good choice, we would have some background knowledge of what coordinate systems are and how they managed in ArcGIS Pro. So we're going to go over the coordinate system a little bit, and it's a lot to learn, and we will mix it in here as the book does, and we will show some basic project coordinates and the coordinates, and the datum. So coordinate systems. Coordinate systems, which is right here, and coordinate systems there. So, which is really nice, and Wikipedia has a lot of information here. So a coordinate system is a mesh of perpendicular intersecting lines superimposed on a surface. Perpendicular intersecting lines. So the point of intersection of any two lines is a unique location. So that's why we have a longitude and latitude. So a point of intersection of any two lines is a unique location, which can be specified with two values. A coordinate pair, the values are measurements from a given reference point in a given unit of measure. So the unit of measure may be an angular unit such as degrees, or length of unit such as feet or meters. So the coordinate system can be applied to any surface, but we are interested in the surface of the Earth. If we represent the Earth with a spherical model, such as a globe, we have a curved surface to deal with. If we represent it with a flat model, such as a map, the surface is flat. So a geographic coordinate system is applied to round or roundish Earth models. So the geographic coordinate system use an angular unit of measure because angles are better for measuring locations on a curved surface. So a projected coordinate system is applied to flat Earth models. Projected coordinate systems use a length unit of measure. So every usable spatial data set has a coordinate system. The location of its features are specified by coordinates that are correct with its own framework, but that would be wrong or observed in another system. 50 degrees of arc isn't the same as 50 meters, which isn't the same as 50 feet. Knowing the coordinates of a point doesn't tell you where the point is on the Earth unless we also know that the coordinate system is. There are many different geographic and projected coordinate systems, as long as two datasets use the same system. Their features will align correctly on a map. Datasets with different systems must be reconciled. This basically means that one dataset's coordinate system must be mathematically converted or projected to the other. So this can be done with the data processing tools. ArcGIS Pro does it automatically when we add layers to a map. What ArcGIS Pro reconciles, however, are the coordinate systems of the layers in the map, not the coordinate systems of the datasets that the layers point to. This reconciliation of coordinate systems in a map is called on-the-fly projection. So now we will see how ArcGIS Pro manages on-the-fly projection of coordinate systems. We will also look at how map display and map measurements change with different geographic and projected coordinate systems. Finally, we will select coordinate systems for the analysis project. So now we will add and check the coordinate system of a dataset. Every spatial dataset has a coordinate system. Now we will see how to find out what is it. So now the issue is we're going to create a new map, and I think this time I'm gonna start from scratch. So this is 3A. I'm gonna do 3A and then 3B. Okay, I'm going to insert a new map. So new map, I will say lesson 3B. This will be A. There. Oh, how come it doesn't like it? So I'm gonna oh, it like it now. It's just slow. How come it It has been that slow. Alright, but it's okay, it doesn't matter. Now we start this and we will open the Los Angeles River and Park Site project, which is right here, and we create a new map and rename it. And in the project pane under Esri geodatabase, we will expand boundaries and jack the state feature class to here. So which state is this one? I'm gonna add it here. So we cannot see anything because we have to move it up on top of the topographic. So in the layer property dialog box of the state layer, we will click source. So in ArcGIS Pro, you have to be familiar. There is a base map always as a default, because for ArcMap you don't have anything. Remember one time I was not familiar with ArcGIS Pro. I put the layer beneath the topographic, so I just thought, oh, how come I cannot see anything? Because the base map is like cover everything. Now in the layer property of the state layer, so we're gonna go to property and see the data source, and click source, which is right here. So for the source, we have everything here. The window for spatial we need to see is WGS. The coordinate system right now is WGS 1984. So the GCS stands for the Geographic Coordinate System. Geographic Coordinate System. GW4 1984 is the World Geodetic System. Geodetic System of 1984, also called WGC 84. So that's something we have to remember. Geographic Coordinate System, and then the World Geodetic System. Under the name of the coordinate system, what system are details giving the essential properties of the system. Its angular unit of measure, degrees of angle, its prime meridian path through Greenwich, so degree of angle, and its datum is WGS 1984. So WGS 1984 is the Geographic Coordinate System. Geographic Coordinate System and the datasets that use them and are set to be unprojected. So if we check the other feature classes in Esri geodatabase, we would find that they all have the same geographic coordinate system. And now we will close the layer property dialog box, hover over the map. So close this, and at the bottom of the it's just right here, so we can see the coordinate system, but we see longitude and then latitude. That's a little bit weird because when we learn latitude and longitude. So here at the bottom of the application window, the coordinates of the pointer are reported in decimal degrees, so it's not in degrees, minutes, and seconds. So the first coordinate, longitude, will tells us the angular position east or west of the prime meridian. The second coordinate, latitude, tells you the angular position north or south of the equator. So in the contents pane, we double click lesson 3B and to bring up the map property, or right click here and we will go to property. Alright, in the map property, so we can go to coordinate system, and then we can see it's a web marker and auxiliary. So coordinate system, we can change it. So now let's look again. In the map property dialog box, we click the coordinate system. I'll confirm that the coordinate system is WGS 1984, which is right here, the same as the state layer. Which one right now? It's I using this one. Add to favorite. Favorites. So now a map is a container for layers in a project. We can insert more maps to manage separate sets of data within the project. So why would you want to do that? It is sometimes a matter of layout. We may want to print a single map sheet that contains a main map, an overview map, an inset map, or some other combination of views. So one crucial function of a map is to enforce the spatial alignment of the layers it contains. When we first add a layer to the map, it adopts that layer's coordinate system as a standard. Any layers added thereafter are converted projected by ArcGIS Pro into that same system. So this process of on-the-fly projection happens automatically as new layers are added. Now we're going to close this. Now project data on the fly. So see how on the fly projection works. We will insert a second map and add a layer that has a different coordinate system from the state layer, and then copy the state layer to the new data frame. To see the content of both data frames at the same time, we must open another map. So then on the insert tab, we will add a second map and name web locator. So new map. I don't need this map. I'm gonna close it out. So, and this map I will say same lesson 3 web locator. Okay. Reposition lesson 3, this one on the right side of here, and by drag the tab in lesson 3 locator to the center of the map. So I can just alright, so I can have it side by side and zoom out a little bit. So cool. And when we release the mouse button, we will have the two maps side by side. Adding the second map is usually down to add a new set of data layers in a new area of interest. So in this case, the second map will allow us to compare two different map projections side by side. So for the view, I'm gonna do is link views. We could do link views and center and share and scale. Perfect. And I don't really need this, so let's explore a little bit so we have a better chance to look. On the map property of the lesson B here, map property, I still have to bring it back. So not catalog, contents pane, which is for this one. So this one is active. Okay, now I'm gonna do is right click on here and go to property, and now we can see it's WGS4 locator ancillary sphere, this projection of the topographic map, and close the property. They have the same, but what I'm gonna do is I might have to change it a little bit, and we will compare them simultaneously and explore a little bit, and it will be very interesting. So in the contents pane on here, we will do is we will right click on the state layer and do copy. Back here in contents, I cannot have two tables of contents, which is so sad. So I'm gonna just copy and go to this one and then just paste. So I have one here as well. In the contents pane of the lesson 3B, we click this and right click on it, copy, and in this one we make it activate and we will paste it. Examine the coordinates of the this one with a Mercator map, and it changed the projection of the state WGS84. The two map layers are identical but display in different projections. So actually right now they are the same projection. I have to go back in here. So go back to properties, and I'm gonna do is this one. So click OK. So now they have different projections now. And we can see the difference now. So even I'm zooming, you can see this is a little flat for the WGS, and this one is a little extended from the north and the south side. With this new projection in Lesson 3B Web Mercator, the base map, which is WGS 1984 Web Mercator Ancillary Sphere, it is now being projected on the fly to WGS 84. Change the coordinate system here back to Web Mercator Sphere and click Project Coordinate System. And I think right now it is the ancillary sphere. So let's, not this one, the Mercator. Right click and go to property. So yeah, this one, let me go down. So even that, I have to find it. So coordinate system, it should be projected coordinate system, and it's under world. And we will go to WGS 1984 web. Okay, click OK. Nothing changes as I mentioned because it's already there. So, and compare the map up here and notice especially the shape of Alaska. This is so flat and this is so extended. We will make a measurement. Coordinate system changes measurements as well as appearance. So that's something we have to make sure that each time we will have to understand. The Mercator projection we are using now is a conformal projection, which means that it shows shapes correctly. Look at the Alaska on the globe and we will see this is true. On the other hand, it distorts areas measurements quite significantly in extreme latitudes. So zooming Alaska, it doesn't matter how far exactly because the two maps are linked. Both will zoom together. On the map tab, we will click measure tool and measure the features. So I'm gonna zoom in here. So zoom out a little bit, and the same way I'm gonna close it out here. And I'm gonna move it to the left a little bit and zooming a little bit more. Now I'm gonna measure it. So remember the measure feature is right here. I'm gonna measure. So under the option here, we will measure, change the area units and mode, click area units. So option area units, and we will do area units. So square miles and square feet. We can do both. And do mode, it will be planner. I think I have to do it this one, mode planner. There. Let's see why this one doesn't work. Okay, so if I do this one, planner, under option for the map 3B, it's right here. We change the units and mode, click units area, and square miles, and click square feet to turn it off. When click mode, we will do geodetic, so which is right here. And click anywhere inside one of the two maps and leave measurement open. So remember, this one is WGS 84 with a geodetic, and this one is Mercator with a planner. Geodetic and with a planner, and open the state layer attributes. So what I'm gonna do is here, open the state layers attribute. So I'm gonna I still have to go back to view and contents. So state, open attribute table. Oh no. Let it flow. Okay, let it flow. So, and we will select the record of Alaska. It should be second one, and scroll all the way to the right to see the square miles attribute. So it's easy to find because Alaska is just with A. I need to resize the window a little bit. Alright, so Alaska, and I'm gonna see, I want to move all the way to the right. So that we have a 279. So we have the value in the table which is correct. That is 581 581,369 square miles. And we can find other values cited in reference source, but they are similar to this one. So it should be the second one. So square miles, which is right here. Yep, 5A1369. But they are similar to this one. But that means that the map measurement is an exaggeration by a factor of more than 5. So at the top of the table window, we will click clear button, close the table. So we will close the table and clear the selection. Clear. And the measurement tool is doing its job correctly. It has measured the area of Alaska distorted by the Mercator projection. The Mercator projection has its virtues, but making area measurement in high latitude, but not one of them. But making area measurements in high latitudes is not one of them. Now we will change the map coordinate system. So we can change the map coordinate system whenever we want, before or after adding the layer. So open the map projection here, and we will click coordinate system, change the projection from this back to, so now I don't know which one this is not the one. So I'm gonna activate this one and go back to view and contents. So here I have the Mercator and I'm gonna right click on it. So now we're going to do is we will change the WGS 1984 to Alaska Albert. So it will be project coordinate system. It will be state plane, I think. No continental folder. So it will go to continental folder, Alaska, North America, and Alaska Albert equal area conic. So I'm gonna click OK, which is found under project coordinate system, continental folder, and North America. So this system, unlike the Mercator, represents area the size of features correctly. So the new coordinate system is applied to the map. Both the base map layer and the state layer are reprojected if we like on the fly. So now if we measure the area of Alaska again, the map should look like the figure. So right here, we have to look. So this is the Albert equal area projection for Alaska. So coordinate systems are organized in folders. The two main folders are geographic coordinate system and projected coordinate system. So both, let me bring this back again. So I don't go back to map, explore. So there. So this geographic coordinate system and projected coordinate system. So both folders contain several subfolders. Both the Web Mercator Ancillary Sphere and Alaska Albert's equal area conic coordinate systems are in the project coordinate system folder. The more we learn about the coordinate system, the more useful this folder structure becomes. So at the outset, it can be a bit overwhelming. For more information, we will see here. We will learn more about it. So how to choose a coordinate system? A suitable coordinate system for the project depends largely on the area of interest. We may also depend on whether we want to preserve a particular spatial property such as shape or area without distortion. So a few systems are common standards. For example, web-based maps typically use the Web Mercator coordinate system. Local area maps within the United States are frequently based on the state plane system, while local area maps around the world, including the United States, often use the UTM, Universal Transverse Mercator system. On the Map Properties Coordinate System tab, we can search for coordinate systems covering only the area of interest. This doesn't mean all the results are appropriate for the map. Systems designed for world maps are displayed with every spatial filter, but may not be a good choice for a local map. We can also enter text, so California, to find coordinate system that include the text of part of their name. This is often a good way to find systems specifically suited to the area of interest. So let's just search California. There. So it didn't show us anything. Usually, that if you work on some area, there are some website will help you to choose the coordinate system. Alright, we're going to talk about more about the geographic coordinate system and a project coordinate system. So a geographic coordinate system, so this one, geographic coordinate system, is based on a spheroid model of the Earth. Sometimes a perfect sphere is used, but usually a slightly squashed oblate spheroid is used to reflect the fact that the Earth bulges at the equator and it's flattened at the poles. So the reference line of a geographic coordinate system are parallax and meridians. Parallax are lines that circle the globe parallel to the equator. Meridians are lines perpendicular to the equator that converge at the poles. By conversion, so the origin of the system, its 0, 0 coordinates, is the intersection of the equator and the prime meridian, the meridian passing through Greenwich, England. And geographic coordinates, commonly called latitudes and longitude values, are measures of angle, not distance. Angles are constant unit of measure on a sphere, whereas distances are not, because meridians coverage. Angle measures are usually expressed in degrees, minutes, and seconds. And a degree has 60 minutes, a minute has 60 seconds. Latitude is angular position north or south of the equator. So the equator is 0 latitude, the North Pole is 90 degrees north, and the South Pole is 90 degrees south. Longitude is angular position east or west of the prime meridian. And the prime meridian is 0 longitude, it's anti-meridian on the other side of the world. It's both 80 east and 180 west. So longitude-latitude pairs defines a unique position on the Earth's surface. So the unique location of the Dodge Stadium, for example, will written like this. So it will be 30. I don't have it here. So let me bring it back. So I'm gonna go back to view, and so bring it back here. Okay. Double click on it, and then I'm gonna go. Oh, actually in here I can do it too. So because I have a bookmark, so I'm gonna go to map and then go to bookmarks and go to Dodge Stadium. So now it zoomed to the Dodge Stadium for me, so I'm gonna just choose no color. So now we can see the Dodge Stadium. What happened to this one? Gonna do this, and I think it was the block data. There. Block and tracks. Yeah, there. Now we can see the Dodger Stadium. And we hover on top. So you can see it from here. So we hover on top. It's 34 degrees and 0.74. It's around 4 degrees. 34 degrees, 4 minutes and 26 seconds. 118 degrees, 14 minutes and 27 west. So we read like this: 34 degrees, 4 minutes, 26 seconds north latitude. 118 degrees, 400 minutes and 14 minutes and 27 seconds west longitude. So west. So for computer calculations, these values are converted to decimals. So these values are converted to decimals. The location of Dodger Stadium in decimal degree, it will be 34.074, or you can say 3 to and 124 degrees. the minus sign is usually used for west longitude and south latitude. So the fact that there are many different geographic coordinate systems is a source of trouble for GIS users. What makes two systems different is the disagreement about the exact latitude and longitude values of particular location. Why is there disagreement about it? In simple terms, it is because different spheroids models of the Earth have been developed over time by different Earth scientists using different technologies. Changing the shape or size of the model ends up changing the coordinates of points on the surface, usually not very much, but sometimes in sensitive applications enough to be of concern. So this issue takes up more detail in the datum, so we're gonna learn datum a little bit more. And now for the projected coordinate system. The Earth's surface can be modeled very well on a spheroid, but not as well except over small areas on a plane. So to make a map, the more or less have to flatten a sphere, which is like squaring a circle, or harder. It cannot be done without critically adjusting these spatial properties and relationships of features on the surface, their shape, size, and relative distance and directions. The name for any such radical adjustment is a map projection. So a projection is a mathematical formula. There are lots of different ones for translating the world into flat space, basically just like 3D to 2D. And now we are looking at just a 2D map. It's being projected. So a map projection introduces spatial distortion. They are various designed to minimize certain kinds of distortion or to distribute it in certain ways over the map surface. Some projections correctly preserve feature shapes but distort other areas. Some preserve areas but distort shapes. Some compromise. Okay. Some have special properties such as keeping true distance measurement from a simple point to or others, or ensuring that courses of constant compass bearing are plotted as straight lines. The smaller area being mapped, the less distortion there is of any spatial properties. Areas up to medium-sized countries, say about the size of Nigeria or Bolivia, can be mapped with distortion so low as to be insignificant for most purposes. So a projected coordinate system consists of a map projection, a length-based unit of measure, an origin point for measurements, and other parameters such as standard lines that define the distortion pattern on the map. Manipulating these parameters is that allows you to customize a coordinate system for a specific area of interest because a projection is applied to a particular spheroid and its definition of latitude-longitude values. A projected coordinate system also includes or presupposes a geographic coordinate system. The idea of project includes both going from a geographic unprojected system to a projected system and going from one projected system to another, sometimes called reprojection. To go from one projected system to another, ArcGIS Pro undoes the map projection, goes back to the underlying geographic coordinate system and applies a new projection to it. So ArcGIS Pro stores thousands of map projection formula and can run these calculations quickly. So it's a magic tool. Some common world map projection and a couple of uncommon ones. So like Mercator, we use a lot. Robinson, we use a lot. And there are some more. We can say Arc5, Bone, and Winkle Triple Fuller, and geographic pseudo projection. When we add an unprojected dataset to a map, that is a dataset that stores feature coordinate systems, such as longitude, latitude values. The data still must be projected in some sense to be viewed as a flat map on the monitor. So ArcGIS Pro, this default pseudo projection has the display properties of a map projection, specifically the plate query, but none of the other properties or parameters of a projected coordinate system. And now we're going to measure it again. Interestingly, that we spend a lot of time just doing the projection. So we measure Alaska again. So equal area projection, which is the Albert equal area conic, is one. Preserve the spatial property of areas or size. So the trade-off is that they don't represent shapes correctly because this projection is customized for Alaska. However, most distortion of all types is pushed outside the area of interest. So now on the Map tab, we click the Measure tool and click Measure Features to measure Alaska again and using this new projection. So the area, so I'm going to close this out and let's double check what is alright, this Alaska Albert equal area. Now we have to do is open attribute table. And we will select Alaska. Why we cannot see Alaska is because we are here in Los Angeles. Okay, so now I can finally zoom to Alaska. And if we scroll to the right, I think the square miles will be a little different. Come on. Alright, so now it will be oh no, come back. So 5A1396. So it didn't change. Let's measure it again. So on the Map tab, we will click the Measure tool and click Measure Features to measure Alaska using this new projection. So I'm gonna go to Measure. So Option and Units Square Miles, yeah, and Mode, Planner, and that's fine. Okay, and then on the Map tab, click this and click Measure Feature to measure Alaska. Okay, Measure Feature. Okay, okay. Oh my god. Can you come on? There, it come out, okay. I don't know why ArcPro is so slow right now. But it's okay. We're gonna resize and drag a little bit. There. I'm gonna drag it to the right. All the way to the right. Oh, it's a lot of data, I know. Okay, so it didn't change. Polygon feature areas. So click Measure Features. So in here, I'm gonna close this out. And Measure Feature. Okay, there. Click this. Alright, so did it calculate it for us? So I'm gonna select this layer. I'm gonna click Measure. There. So yeah, Measure Feature. So right click on this Measure Features and then I select Alaska. So now it gave 58133 square miles, and it's different now. And let's look at this and remember they synchronize. Okay. Alright, let me go to Explorer. Yeah. So now I'm gonna zoom out a little bit. So see, we have these two together, and this coordinate system is obviously unsuitable for a world map. It doesn't know the whole world. For one thing, the price for mapping Alaska with very low distortion is that places such as Australia and South America are severely distorted. Which is fine as long as we keep the map zooming Alaska. But it's good for Alaska, but not good for the South Hemisphere. Now we can summarize how things stand with the layers in this data frame. So the geographic coordinate system of the state layer is GCS WGS 1984. It has no projected coordinate system. The projected system of the base map layer is Web Mercator. Its underlying geographic system is GCS and WGS 1984. The map has been set to the Alaska Albert Equal Area Conic projected system. Its underlying geographic system is GCS and North America 1983. So the state and base map layers have been projected on the fly into the Alaska Albert system. So no matter how often we change the coordinate system, ArcGIS Pro keeps the data in alignment, which is really nice. And we will change the project back in into the. So I have to go back. So go back to View and Table of Contents, and I'm gonna right click on this, and probably you already have the favorites, I think. Yeah, so that's the one I like. And which one we will change it back to the WGS 1984 Web Mercator Ancillary Sphere under Projected World from Alaska Albert Equal Area Conic. And on the View tab, we will click Link View on turn off this, and we will click Close it out. Now we will add another layer. Now we can get back to True Area in Interest. So now we will zoom to the Los Angeles River and turn off the. I don't even remember where's my Los Angeles River. It was in the yeah. Okay, then I'm gonna go zoom to layer. There. So we have to copy that layer, and we will zoom to the Los Angeles River. So now I'm gonna bring it back. Los Angeles River, we can just copy and close this out and paste it. Now we have a Los Angeles River. And we zoom to the Los Angeles River and turn off the stay layer, which I did. So a coordinate system meant for Alaska or the world isn't appropriate for Southern California. Local mapping needs across the United States are served by a system called the State Plane Coordinate System. And this isn't a single coordinate system for the entire country, but a patchwork of systems, each of which covers a state or part of a state. Together, they assure that for whichever part of the country we want to map, we get uniformly low distortion. So now California is divided into 6 states plane zones, which Los Angeles falls into Zone 5. And now the state plane coordinate system divides states into zones and applies a locally optimized coordinate system to each zone. Vertical zones are based on the transverse Mercator projection. Horizontal zones are based on the Lambert conformal conic projection. So we changed the map coordinate system. We will change the map coordinate system again, and this time to state plane California Zone 5. So which I'm gonna change it now. So it's in a state plane. I think I will change it everybody. So state plane. So for state plane, 1983 US feet. Zone 5. Zone 5. California, 1983, Zone 5. California, State of California, Zone 5. US feet, 0405. Perfect. Okay, click OK. Let's back up a little bit. There. So, there. So, we expand the coordinate system of NAD 1983 state plane, California V FIPS 0405 feet. This coordinate system must be used by the river. Okay, so for the layer, and it's not here, so every layer should apply now. Strictly speaking, it is a coordinate system of the Los Angeles shapefile, and click the layer name to highlight it. So this set the layer name to highlight it. So this resets the current coordinate system of data frame. So the state plane coordinate system for California 5 is a projected coordinate system based on a Lambert conformal conic map projection. Its underlying geographic coordinate system in North America 1983. This is different from the WGS 1984 system used by both the state and base map layers. So now go to property and source, spatial reference. Oh, so the datum, this one coordinate system didn't change it yet, so we're gonna highlight it, go to property, and we will click OK again. And go to property, spatial reference. Let's see. Source. I think I have to reproject it in this case. So click the layer name and highlight it. I did, and this reset the current coordinate system of the data frame. The state plane coordinate system for this is a project coordinate system based on the Lambert conformal conic map projection. So its underlying geographic coordinate system in North America 1983 is different from the WGS 1984 system used by both the state and base map layer. So the map should look like this figure. The state plane coordinates for California zone is the one we will use for the analysis. Now we're going to save everything, and of course later we will have to explore a little bit, and we will talk about datum next time. So for the spatial reference, I think the only thing is we could reproject it using the tool, and then when you go to the spatial reference, and then the geographic coordinate system will change. So let's do it then. Go to analysis and tools. So project. Define projection. So we will do Los Angeles River. Coordinate system we will do. Oh, I think maybe favorites has it. No. State plane, remember, and 1983 US feet. And California, zone 5. Click OK. And then run. What happened to the Los Angeles River? So what I'm gonna do is we'll save this layer, data, export features. So I'm gonna save it first, and then I will reproject it. So output, where did I save it? Okay, so it will be Los Angeles River. Let's Let me put into the geodatabase. Okay, it's in the geodatabase. Click Run. There. So now I have it. Okay. Now I'm gonna bring this back again. Define projection. Yeah, projection, define projection. There. So I'm gonna do this, and yeah, now I can do the projection. So it's in state plane and 1983 feet. There. And California. Run. So okay, so I have this layer, and let's see again. Right click on it, go to property, and then spatial, and now we can see it's in California. And this one, let's see, go to property, spatial reference should be, yep. Okay, that's how we change its projection. Okay, cool. And we will start with the data and then continue to build the database. Thank you so much. See you next time.